So in the last class, we did talk about operators, the momentum operator and the energy operator, right? If you talk about the momentum operator, and again, if you are talking in 1D, then we did find out that momentum operator is given by this expression. Similarly, your energy operator is given by this value. Now, if you remember from electromagnetic theory, now you might be able to justify why these are called operators, because these terms do not have any meaning unless they act on some wave function. This is your momentum operator in 1D. Of course, if you talk about this being in 3D, in the case of 3D, this momentum operator would be given by x unit vector curly by curly x plus y unit vector curly by curly y plus z unit vector curly by curly z, if you are talking in 3D. But in most of the discussions that we are going from now onwards in the next 2 lectures or so, we will be just sticking to the 1D cases only. So for you, it is sufficient to know that your momentum operator would be given by this expression here. Energy operator doesn't matter if you are in 1D or 3D, because you are taking derivative with respect to time. And then we said that because your total energy is sum of kinetic energy and potential energy. Kinetic energy is nothing but P square upon 2m. Potential energy, let's denote your potential energy by U. In both sides, if you could multiply it by psi, plug in the value of energy and momentum operator, what you will get would be something like this. Oh, sorry, it's T here. Minus h bar square upon 2m curly square by curly x square of psi plus u psi. And it is obvious that your psi is going to be a function of x and t. We are talking about your wave equation being a function of only one position variable and time here. Because now your wave function here, I haven't written here, but this wave function is a function of position coordinate and time coordinate. That is why this is called as time dependent Schrodinger wave equation. And this is the basis of quantum mechanics. क्वांटम मैकेनिक्स में आपको कोई भी प्रॉब्लम दी गई है, इवन जो हम लोगों ने SHM सोल्व किया था, इवन दो सिंपल SHM प्रॉब्लम्स आल्सो, प्लग इन द वैल्यू ऑफ पोटेंशियल, यहाँ पे आपका जो भी कोई पोटेंशियल है उसकी वैल्यू यहाँ पे प्लग इन कीजिए, आपके पास में एक सेकेंड ऑर्डर डिफरेंशियल इक्वेशन होगी, आप इसको सोल्व कीजिए, साई का वैल्यू जो है वो आप यहाँ पे कैलकुलेट फाइंड आउट कर सकते हैं अगर आप इस डिफरेंशियल इक्वेशन को सोल्व कर देते हैं. और अगर आपको एक बार वेव फंक्शन मिल गई है, then as we said yesterday, your wave function contains all the information about the particle. अगर आपको वेव फंक्शन मिल गई है, आप मोमेंटम की एक्सपेक्टेशन वैल्यू कैलकुलेट कर सकते हो, एनर्जी की एक्सपेक्टेशन वैल्यू कैलकुलेट कर सकते हो. And let me remind you now that in the yesterday's class, we did talk about the expectation value of position, which we said that you have to integrate from minus infinity to plus infinity, psi star x psi. And again, I'm just sticking in 1D now. And this will be equal to minus infinity to plus infinity, psi star, here psi dx. If you have already normalized your wave function, then this term is equal to 1, and this would be simply equal to minus infinity to plus infinity psi star x psi dx. If you want to calculate the expectation value of momentum now, it will be minus infinity to plus infinity psi star p psi dx. And if wave function is not normalized, then you need to calculate this denominator also. And if you have normalized the wave function, that case your this value will be equal to 1, and आपकी यहाँ पे expectation value होगी. P आपका operator है, operator की value अगर आप यहाँ पे plug in कर दोगे, you will get minus infinity to plus infinity psi star. The value of P is minus iota h bar curly by curly x, minus iota h bar is constant, so you will have curly psi over curly x into dx. And again, if you haven't normalized, you will have the denominator also. The ordering of the terms is important. You cannot shuffle around the terms here and there. That means your momentum operator has to always lie between psi star and psi. अगर आप अपना मोमेंटम ऑपरेटर इधर लेके आते हो तो वो मीनिंगलेस हो जाएगा, क्योंकि आपका करली वाई करली एक्स किसके ऊपर एक्ट करेगा? यू डू नॉट हैव एनीथिंग टू एक्ट अपॉन। अगर आप अपना मोमेंटम ऑपरेटर एक्सट्रीम राइट में लेके आ जाते हो तो, और अगर आप अपना मोमेंटम ऑपरेटर एक्सट्रीम लेफ्ट में लेके आ जाते हो, देन यू विल सिंपली हैव द psi star psi integrated over curly by curly differentiated over curly by curly x and integrated over dx. वो वाली जो टर्म है वो भी आपकी यूजलेस टर्म होगी. So the sequencing is very important. You always have psi star in the beginning, then you have the operator, and then you have the psi, the wave function as it is. Now, if you want to calculate the expectation value of the energy, it would be given by this expression. Psi star, energy, operator, psi, dx, minus infinity to plus infinity, psi star, psi, dx. Energy operator is iota h bar, and here you will have minus infinity to plus infinity, psi star, curly psi by curly t into dx, minus infinity to plus infinity, psi star, psi dx. This is how you can calculate the expectation value of energy in this case. I'm talking about position, energy and momentum. If you have any random operator, या आपके पास में कोई भी random variable है, which let's say you have any function and आपने जो function लिया है, that is a function of position as well as momentum. आपने कोई ऐसा function choose कर लिया है. You can calculate the expectation value of that function also in the similar way. You do psi star, then you simply do gxp and then psi dx minus infinity to plus infinity, psi star, psi dx. We will calculate we'll do the particle in a box or infinite well, and then I'll numerically solve the expectation value of position or momentum. Usually it is asked in the exam also many times that calculate the expectation value of position or momentum for a particle in a box in the ground state or first excited state or second excited state or so on. I'll calculate one of the values and show you how those kind of calculations are done so that you can understand these expectations value in a better way. Now we did talk about the Schrodinger wave equation, which we said that is going to be something like this. Minus h bar square over 2m curly square psi over curly x square plus u psi. This is your time dependent Schrodinger wave equation. Now I'm going to tell you, using this time dependent Schrodinger wave equation, how we can derive the time independent Schrodinger wave equation. Because here your psi is a function of both x and t, that is why this is your time dependent Schrodinger wave equation. For a specific cases, for example, the cases in which, and let me write first the title. If you look at this expression here, this side you have a derivative with respect to time, this side you have a derivative with respect to x. So there is no mixing of x and t except this last term here. Because in the last term, you do not know if you are this potential here, is it simply a function of position or is it a function of position and time both? I'm repeating that again. If you look at the terms in this expression here you have simply derivative with respect to time, here you have simply derivative with respect to x. So there isn't much mixing of x and t. But if you look at the last term here, the potential energy here, we do not know if this potential energy is simply a function of x or is this a function of x and t both. if we consider the cases in which your potential depends only on position, that means it is independent of time. And for example, if you take particle in a box, that in that particular case, your potential is going to be independent of time. It will simply have dependence on position also. You can assume that if you have a hydrogen atom में क्या होगा, आपका न्यूक्लियस का अट्रैक्टिव फोर्स एक्ट करेगा, उसके चारों तरफ इलेक्ट्रॉन मूव कर रहा है, इलेक्ट्रॉन जिस पोटेंशियल में मूव कर रहा है, दैट इज काइंड ऑफ टाइम इंडिपेंडेंट पोटेंशियल. यू कैन सिंप्लीफाई इट इन दैट वे आल्सो, क्योंकि आपके हाइड्रोजन में सिर्फ एक प्रोटॉन है, तो एक प्रोटॉन की वजह से जो पोटेंशियल है वो पोटेंशियल है ही है. So you can say that basically your electron is moving in a potential which is going to be independent of time, and it is only going to be a function of position also. In those cases, what we can do is that rather than solving this time dependent Schrodinger equation, which is slightly complicated, we can break it down into two parts, which one of which will be a function of time, the another one will be the function of position. For example, in that case, what I can do is that I can write it into two parts, one of which is a function of position only, and the second one is a function of time only. You can do that. And that is only in the cases when your potential does not depend on time. Now, if you remember, for a free particle in yesterday's class, I say that the wave function for a free particle is given by this form, kx minus omega t. We can also break it down into two components, one and the second one. This is the function of position only. A is some random constant, normalization constant. The second term is a function of time only. Now, if you have a potential that depends only on the position, let's say this is your phi x and this is your ft here. What would happen if, I'm repeating that again, if you have the potential which only depends on the position, then you can break the equation into two parts, one which is a function of position only, the second which is a function of time only. And now because your potential depends only on the position, तो अगर आप इसको फ्री पार्टिकल के साथ में कंपेयर करो तो सिर्फ ये वाली जो टर्म है वो चेंज होगी, जो टाइम वाली टर्म है वो आपके फ्री पार्टिकल जैसी ही रहेगी, even if there is some potential acting on the particle. Remember, अगर आप फ्री पार्टिकल की बात कर रहे हो, in that case your potential is basically zero. आपका पोटेंशियल जो है वो जीरो है. Now I am saying that even if your potential is non-zero and वो पोटेंशियल सिर्फ पोजीशन पे डिपेंडेंट है, तो वो सिर्फ जो पोजीशन वाली टर्म है उस पे ही अफेक्ट करेगा, उसकी जो टाइम वाली टर्म है वो एज इट इज रहेगी. That means I can write this as phi x, और जो टाइम वाली टर्म है, even though now your particle is sitting in a potential, ये जो टाइम वाली टर्म है वो सेम रहेगी जो कि आपके फ्री पार्टिकल की थी. This would still be minus I omega t. That means I can write it further as phi x is equal to e raised to power minus, from yesterday's class, e is equal to h bar omega. Omega I can write it as e over h bar into t. This is my psi xt. Now you have to do a very simple calculations or very simple mathematics here is involved. Simply plug in the value of psi xt into this equation 1. Equation 1 में आप psi xt की जो वैल्यू है वो प्लग इन कर दीजिए. आप टाइम की जो टर्म्स है उसको सेपरेट कर पाओगे, जो पोजीशन की टर्म्स है आप उसको सेपरेट कर पाओगे. Let's see how I can do that. This is if your wave function, अगर मैं इक्वेशन 1 में प्लग इन करना चाहती हूँ तो मेरे को एक तो करली साई बाई करली टी चाहिए, एक मेरे को करली स्क्वायर साई बाई करली एक्स स्क्वायर चाहिए है. ये वाली जो दो टर्म्स हैं, I need these two terms here, which is easy to calculate. अगर यहाँ पे मैं करली स्क्वायर साई बाई करली एक्स स्क्वायर करती हूँ एंड दिस इज अ फंक्शन ऑफ एक्स एंड टी, इसका तो पोजीशन से कोई लेना देना नहीं है, it doesn't have anything to do with the position, so what you will get is d square phi over dx square. I am writing now d rather than curly because your phi is a function of x only. There are no other variables involved here, and your this term would stay as it is. This would be the second order derivative with respect to position. You also need curly psi by curly t. If you do that, curly psi by curly t. Now this term doesn't have anything to do with time, so it will stay as it is. You need to take the derivative of this exponential term with respect to time. So exponential will stay as it is. और इसकी पावर का अगर आप with respect to time अगर आप लोगे, you'll get minus iota e over h1. Now we simply have to plug in these two values into equation 1. If you do that, let's see what you will get in that case. So your equation 1 will be iota h bar. You had curly psi by curly t. Curly psi by curly t is nothing but phi x e raised to power minus iota e upon h bar t. So this is going to be phi x e raised to power minus iota e upon h bar t and minus iota e upon h bar is equal to minus h bar square upon 2m curly square psi by curly x square, which is going to be this expression here. So this would be equal to minus h bar square over 2m e raised to power minus iota e upon h bar t d2 phi over dx2, which was this term, plus u psi. Now u is a function of position only, and psi we defined as phi x e raised to power minus this term. So I can write phi of x e raised to power minus iota e upon h bar t. If you look at this expression here, there are common terms which you can get rid of. And that common term is basically your e raised to power minus iota e upon h bar t. You can cancel it on both sides. What you will get would be minus h bar square over 2m. I'm writing this side now on this side. d2 phi over dx2 plus u, which is a function of x, phi, which is a function of x, is equal to iota square minus 1. Minus minus would become plus here. So you will have e upon h bar into phi of x. And then there is iota, there is one extra h bar here, basically. Let me repeat that. Minus iota square plus 1 हो गया, h bar यहाँ पे है, h bar आपका यहाँ पे है. I can cancel this h bar with this h bar. So this equation, if you now look at this equation here, you have an equation which is only a function of phi x. It does not have time anywhere, and this equation is called as time independent Schrodinger wave equation. The reason, because it does not have any time dependence. And this is how, if you start from time dependent Schrodinger wave equation, you can derive the expression for time independent Schrodinger wave equation. And this equation is going to be comparatively easy to solve because now you simply have a function which is a wave function which is a function of position only rather than being a function of position and time, both of the variables. So again, any kind of potential you are given, plug in the value of that potential here. If that potential is a function of position only, you have a second order equation and you know very well how to solve this kind of second order equation. You can get phi x. If you know the phi x, अगर आपको phi x पता है तो आप फिर यहाँ पे psi xt भी कैलकुलेट कर सकते हैं. You simply have to add an additional term of e raised to power minus I omega t. आपको psi xt मिल जाएगा. psi xt मिल गया तो उसके बाद में आप उस पार्टिकल से रिलेटेड सारी इंफॉर्मेशन जो है वो कैलकुलेट कर पाएंगे, चाहे वो उसका मोमेंटम की एक्सपेक्टेशन वैल्यू है, पोजीशन की एक्सपेक्टेशन वैल्यू है या एनर्जी की एक्सपेक्टेशन वैल्यू है. वो सारी की सारी इंफॉर्मेशन जो है वो आपके पास में अवेलेबल होगी. So this is how the quantum mechanics works. This is the fundamental equation जहां से आप हमेशा स्टार्ट करते हो. इस इक्वेशन को सोल्व करते हो, wave function आप extract करते हो. Wave function contains all the information about the particle and you can calculate all the parameters related to that particular particle by using the wave function of that particle. Now there is something which is called as eigenvalue, eigenfunction. Suppose you have any operator, उस operator को आपने wave function पे operate करा दिया. You will get something here and then you will get something here also. Now what you are going to get here, it could be some constant here. Let's call that constant as a, and you might get this wave function as it is here, or it could be that you can get the constant here, and rather than getting phi here, you will probably get something, another wave function which could be psi1 here. An example of simple example of this is, let's say I'm saying that my phi is equal to a sin kx. अब अगर आप इसके ऊपर मोमेंटम ऑपरेटर अप्लाई करते, so what would happen? Momentum operator minus iota h bar curly by curly x of a sin kx minus iota h bar, a आपका बाहर आ जाएगा, k भी आपका आएगा, साइन का डिफरेंशिएशन आपके पास में कोसाइन kx आ गया. So you have something a cos kx, बट आपका जो वेव फंक्शन था वो तो a sin kx था, right? Now rather than having the momentum operator, right, let's say you had the momentum square operator. अगर आपका momentum square operator होगा तो उस केस में आपके पास क्या होगा? h bar square, right? And then you will have curly square over curly x square of a sin kx. अब अगर आप इसका 2 टाइम डेरिवेटिव करोगे तो आपके पास में आ जाएगा a square k square and you will probably get minus here and then you will get sin kx back. You shouldn't have even a square, you will simply have a. Sorry about that, क्योंकि a constant आप उसको बाहर निकाल दोगे, sin kx का एक बार डिफरेंशिएशन करोगे तो k टाइम cosine kx आएगा, cosine kx का आप फिर से डिफरेंशिएशन करोगे तो minus k sin kx आएगा. If you look at this expression here, what I can get is I can rewrite it as simply this form also. So you have some constant here और आपकी wave function जो है वो आपको as it is मिल गई है. So what does this physically mean? This means that every time this operator operates on this wave function, you will not get something meaningful out of it. Let me repeat that. Not every single time this operator is going to act on this wave function, you will not get a meaningful output. There are going to be certain values and those certain values are the values for which this wave function remains the same. अगर ये आपका wave function same रहता है, yes, if you started with phi here and you end up with phi here, which was what happened in the second case here, in that case you say that कि ये वाला जो आपका operator है, ये ऑपरेटर जब इस वेव फंक्शन पे एक्ट करता है तो ये वाली जो वेव फंक्शन है यू कैन कॉल दिस एज आइगन वेव फंक्शन। और अगर आपको यहाँ पे जो कांस्टेंट मिलता है उसको आप बोलोगे दीज आर द आइगन वैल्यूज ऑफ दिस वेव फंक्शन। This means that now you can say that this p operator when it acts on the psi, so this wave function here is not an eigen wave function for the momentum operator. Momentum operator के लिए eigen wave function नहीं है, but this wave function is an eigen wave function for p square. आपके momentum square वेव फंक्शन के लिए ये एक आइगन वेव फंक्शन है क्योंकि आपको कुछ कांस्टेंट मिलता है एंड यू गेट द वेव फंक्शन बैक एज इट इज। You can take another example. For example, you had another wave function which is of the form c e raised to power 2x. अगर आप इसके ऊपर मोमेंटम ऑपरेटर अप्लाई करते हो, so what you will get, 2 आपका बाहर आ जाएगा, 2 times c e raised to power 2x, and of course you will have minus iota h bar also. ये आपका वेव फंक्शन आपको एज इट इज वापस मिल गया, सो यू विल गेट 5 हियर। सो दैट मींस इस वेव फंक्शन के लिए अगर आप इस वेव फंक्शन की बात करते हैं और इसके ऊपर अगर आप मोमेंटम ऑपरेटर एक्ट कराते हो, यू आर गेटिंग द वेव फंक्शन बैक हियर। दैट मींस दिस वेव फंक्शन इज एन आइगन वेव फंक्शन ऑफ मोमेंटम ऑपरेटर, और आपको यहाँ पे जो वैल्यू मिली है विच इज माइनस आयोटा एच बार इंटू 2, दिस इज गोइंग टू बी योर आइगन वैल्यू। और यही जो पर्टिकुलर वैल्यूज जो हैं जहां पे आपको यहाँ पे वेव फंक्शन एज इट इज मिल जाता है जब आप ऑपरेटर ऑपरेट कराते हो उस पर्टिकुलर वेव फंक्शन पे, वही आपके मीनिंगफुल स्टेट्स होती हैं। रेस्ट ऑफ द स्टेट्स आर नॉट मीनिंगफुल। दिस इज द मीनिंग ऑफ आइगन वैल्यू एंड आइगन फंक्शंस हियर। नाउ लेट्स टॉक अबाउट, there is something we said that if you go to the previous slide here, if you look at this side here, अगर आप इस साइड के इस वाले पोर्शन की तरफ देखते हैं, सिर्फ लेफ्ट हैंड साइड here, this is called as your Hamiltonian operator, which is going to be given by this term. Of course, your wave function is not going to stay now, and this is called as Hamiltonian operator. जब ये Hamiltonian operator wave function पे act करेगा तो आपको energy मिल जाएगी, and these will be your energy eigenvalues. And ये आपके आइगन फंक्शंस होंगे, and this is, let me repeat again, called as Hamiltonian operator, which will have kinetic energy and potential energy term, which basically corresponds to the energy of the system. And this, the fact now I'm saying that only those values are allowed in which you get the wave function back as it is. That means अगर आप यहाँ पे हैमिल्टनियन अप्लाई करोगे, आपको यहाँ पे कुछ सर्टेन वैल्यू ऑफ एनर्जी जो है वो अलाउड होंगी, which basically means that अब आपका एनर्जी जो पार्टिकल की होगी वो कंटिन्यूअस नहीं होगी. There will be discretization of the energy of the particle, which does not happen in the classical mechanics. I'll come back to discretization of energy again when we are going to talk about particle in a box. And now let's talk about that particle in a box. Particle in a box or in infinite potential value. Let's first draw the figures so that it's a bit clear here. This is your x-axis. This is your potential. And this is, let's say, x is equal to 0. This is x is equal to L. Now, we are talking about an infinite potential well. That means this becomes infinite at x is equal to 0 and at x is equal to L. And you have a particle which is trapped in this infinite potential well. आपका जो particle है इस infinite potential well के बीच में trapped है. Now, if you think about it physically, the particle cannot exist here. It cannot exist here. The reason is that because you are saying that the energy of the particle is going to be infinite. It's kind of constant at infinity here. So if your particle has to exist outside this box, then its energy has to be infinite. And you know that your particle, any particle cannot have an infinite amount of energy into it, right? Or you can also consider it that you have a particle which is basically trapped in a box. आपका एक particle है जो box में trapped है. That means आपका particle यहाँ पे नहीं exist कर सकता है और यहाँ पे नहीं exist कर सकता है. You can treat it other way around also. But if you take this kind of system where you are saying that the energy from here to here, from this point to this point, your potential is 0 और इस point पे जाते ही suddenly आपका potential infinite हो जाएगा और इस point पे भी जाते हुए आपका जो potential है वो suddenly infinite हो जाएगा. That means कि आपका particle के साथ में जो wave function associated है, अगर मैं इस particle के साथ में associated wave function calculate करूं वो आपकी 0 हो जानी चाहिए at x less than equal to 0 or x greater than equal to L. L पे आपकी particle wave function 0 हो गई. That means probability of finding the particle is 0, right? क्योंकि हम ये claim कर रहे हैं आपका particle यहाँ पे exist ही नहीं कर सकता क्योंकि यहाँ पे आपका potential है वो infinite है. And we know कि आपके particle के पास में infinite amount of energy is not possible. Hence, the probability of finding the particle is 0 at the boundary as well as outside the boundary. You cannot have the particle anywhere here or here or here. It has to be only in between these two limits, x is equal to 0 and x is equal to L. That means your wave function is 0 at x less than equal to 0. That means your wave function is 0 on this side and your wave function is 0 from here onwards. We are also assuming that the walls of this potential are infinitely hard, so that whenever particle collides here and it returns back, there is no loss in the energy of the particle. Otherwise, in a real world, if you assume, of course, if your particle is going to collide with the wall, it is going to impart some amount of energy to the wall. But we are assuming an idealistic case just to give you a feeling what would happen to the energy of the particle, wave function, etc. We are going to assume that these walls are infinitely hard so that the energy of the particle is going to be conserved here. You know your Schrodinger wave equation. This was your time independent Schrodinger wave equation from here. Because your potential is constant here. Your potential does not have any time dependence. Hence, I can start with the time independent Schrodinger wave equation itself. Now, we have said that, look at this axis here. If you talk about the limit between x is equal to 0 and x is equal to L, your potential is 0 here. U is equal to 0 here. And then it increases in this direction. So between x is equal to 0 and x is equal to L, your U is equal to 0. That means you can rewrite this equation in this form also. Because your U is equal to 0 inside the well. यहाँ पे आपका u है वो बेसिकली 0 है, एंड इसके एकदम बाहर आपका पोटेंशियल है वो इनफाइनाइट पोटेंशियल है. Reshuffle these terms, you can write these as d2 phi dx2. यहां से इधर लेके जाओगे, you will get minus 2 me h bar square phi. I'm not writing phi is a function of x. Then take this term also on the other side and you will get something like this. This is the equation that you need to solve. Remember I said you always start with श्रोडिंगर इक्वेशन. हमेशा आप उसको सोल्व करते हो, उसको सोल्व करके आप वेव फंक्शन कैलकुलेट करते हो. एक बार आपने वेव फंक्शन कैलकुलेट कर दी, देन यू आर सेटल्ड इन क्वांटम मैकेनिक्स. यू डू नॉट नीड टू bother about anything else because all the information is contained in the wave function. If this equation here, which is d2 phi over dx2 plus 2me h bar square phi is equal to 0. Many times this term is also called as k square. I'm not going to do that because I don't want to confuse you. This k does not have anything to do with wave number. इसका wave number से कोई लेना देना नहीं है. This k is not also your spring constant. This is some random another variable जो आपने define किया है. So many times it is, this term is defined as k square also. You can do that if you want to do that. I think in many books this is defined as k square. If you remember from the very first unit, we said, remember we said f is equal to minus kx in your simple harmonic motion. And from here you get something d2x over dt2 plus k over m x is equal to 0, जिसको कि आपने यहाँ पे ओमेगा स्क्वायर किया था. सो एंड फिर हमने कहा था कि इसका अगर आप सॉल्यूशन लोगे दैट वुड बी a कोसाइन ओमेगा t. अगर आप मोस्ट जनरल सॉल्यूशन की बात करते हो इट वुड बी प्लस b साइन ओमेगा t, वेयर a एंड b आर रैंडम कांस्टेंट्स जिसकी आप वैल्यू कैन कैलकुलेट फ्रॉम द इनिशियल कंडीशन और अनदर पैरामीटर्स व्हिच आर गिवन टू यू. वहां से आप ये वैल्यूज कैलकुलेट कर सकते हो. Similar is the case here. You can definitely compare these two equations now. If the solution of this equation was given by this expression, that means the solution of this equation would be given by a cosine of omega. Omega was this expression, which will be now square root of 2me h bar square t. यहाँ पे क्योंकि आपका डिनोमिनेटर में t के विद रिस्पेक्ट टू डिफरेंशिएशन कर रहे थे, यहाँ पे आप डिफरेंशिएशन विद रिस्पेक्ट टू x कर रहे हो, प्लस b साइन स्क्वायर रूट ऑफ 2me h bar square x. This will be your most general solution. A and b are the constants. Now we are going to focus how do we decide the value of a and b. हम a और b की जो वैल्यू है वो कैसे हम डिटरमाइन करेंगे. If you look at this wave function, let me plot that potential again. We said that this is our potential from x is equal to 0 and x is equal to L. This is your x-axis. This is your potential axis. Remember, I said your wave function has to vanish at x is equal to 0 and at x is equal to L. That means if I put the value of x is equal to 0, if I put the value of x is equal to L, this should become equal to 0. क्योंकि आपका पार्टिकल यहाँ पे एग्जिस्ट कर ही नहीं सकता है. क्यों नहीं एग्जिस्ट करेगा? Because you are then saying that the potential of the particle is infinite, its energy is infinite, which is physically not possible. Your particle cannot have any finite amount of energy. So your particle cannot exist here. If your particle cannot exist here, the probability of finding the particle at these points has to be equal to 0. And if the probability of finding the particle is 0, that means your wave function itself has to be 0. Put the value of x is equal to 0 and x is equal to L. Put them equal to 0 in this equation number 2 here. Let's first put phi x is equal to 0. अगर आप x को 0 put करते हो, a cosine of ये जो constant term है multiplied by 0 plus b sine of 0. साइन 0 0 होता है, आपके पास में यहाँ पे सिंपली a बच गया है. So that means from here you will simply have the cosine term in your expression. Am I correct here? Anyone?
Yes, ma'am.
I just said that there will be only the cosine term in this expression now. Am I correct in saying that? If I say that at x is equal to 0, you will get a cos 0 plus b sin 0. Sin 0 0 hota hai. You will simply have a here.
Equal to 0.
A is equal to 0. क्योंकि आपकी wave function at x is equal to 0 has to be equal to 0. So if your a is equal to 0, आपके पास cosine नहीं, आपके पास में सिर्फ sin वाली term बचेगी. That means एक condition आपने apply की. Now you know that your phi x is equal to b sin square root of 2me h bar square x. अब हमारे पास में सिर्फ b की वैल्यू पता करनी रह गई है, क्योंकि एनर्जी नोन होगी, मास पार्टिकल का नोन होगा, x आप डिसाइड करोगे कि आपको किस x की वैल्यू पे उसकी जो वेव फंक्शन है वो पता करने हैं. So now we are left with the job to find out the value of b, and we'll do that in the next class. I'll stop here. Anyone has any doubt in today's class?
Ma'am, why is it called infinite potential well?
Because the depth of this potential here, अगर आप यहाँ से यहाँ तक की इसकी जो डेप्थ मेजर करोगे वो इनफाइनाइट है. यहाँ पे आपका पोटेंशियल की वैल्यू 0 है, यहाँ पे आपके पोटेंशियल की वैल्यू इन्फिनिटी है. That is why it's an infinite potential well.
Okay.
Anyone else has any other questions? To remind you, you have a quiz today, right?
Yes, ma'am.
Okay. Best of luck for your quiz then. And then I'll see you on Friday.